Hello, in this video we will be looking at a particular way to impose boundary conditions for potential flows, the method of images. Alright, so let's imagine that I have a vortex placed here in, say, in the middle of a domain, or at a certain position. That vortex is generating a flow in this direction, like a rotating flow around this vortex, around the center point. And let's imagine that this vortex, I want to impose on top of this vortex boundary conditions. For instance, I want to impose a wall in this direction, or maybe I want to impose a wall in this direction, in the y direction. So that's what the method of images allows you to do. It's going to allow you to impose a wall either in this direction or in this direction. So let's just, for the sake of the example, let's just write down the complex potential for a vortex. So that potential is going to be f of z. It's minus I gamma over 2 pi, where gamma is the circulation, times the logarithm of z minus v, where v is going to be the coordinate of my vortex. So v, for instance, equals a plus ib, is the location of the vortex. And I'm going to use this example throughout the exposition of this method as a way to illustrate what the method of images is. Okay, so we do have two possibilities here. So we have a wall at y equals 0, for instance, or a wall at x equals 0. And what you can do is just, change the 0 for any value that you want, for any location that you want along the horizontal or vertical axis, by just resetting your variables in your problem. So it really boils down to just checking these two cases, understanding these two cases. So the first case is the wall at y equals 0. And the way to impose this is to apply the following formula. So that's going to be my new potential, my complex potential. And what I'm going to do is take the potential that's for the flow that I'm interested in, and to this potential I'm going to add the same potential, but it's going to be f of the complex conjugate of z, and I'm going to take the complex conjugation of the whole thing. Okay, so I'm taking my original vortex and I'm adding another vortex that's effectively going to be reflected against this y equals 0 wall. Okay, and well, the sum of these two potential is going to be a potential who's got y equals 0 as a streamline. This is what we can do in potential flow theory. We cannot impose no-slip boundary conditions because there is no friction in our flow. However, we can impose free slip boundary condition, or rather that the wall is a streamline. Okay, so let's check what this is. So if I write down z to look at what the horizontal line corresponds to, so let's check if I write down z equals x. So z equals x is the equation of my horizontal line. Then w of x is going to be equal to f of x plus, and I'm going to take here f of x bar with an over bar. X is, and I'm going to write down here that I'm always going to write down my complex numbers as z equals x plus iy. Okay, so x is really a real part here. And so this is going to be just f of x plus f of x. The complex conjugated of the real number here is a real number over bar. Okay, and so what I have here is a number, it's a complex number, plus the complex conjugation of this complex number, which, well, ultimately is a real number, right? So what I have here is that w of x is real. And what that means is that, well, the complex potential is equal to the gradient of velocity plus I times the stream function. That means that here the stream function for x equals 0. Okay? And so what that means, in other words, is that, z equals x is a streamline. And so we've just verified by writing this for no matter which potential that we have here, well, then the result is a flow, the corresponding flow for which z equals 0 is a streamline. Okay, so let's just take an example here, the example of my vortex that we had here. So this vortex was writing f of z is minus I gamma over 2 pi log of z minus v. So what I'm going to do here is write down what the application of this method of images for a wall at y equals 0 is for this particular case. So I'm just writing down f of x, so it's minus I gamma over 2 pi log of z minus v. And on top of this, I'm going to add plus f of z bar over bar. So I've got plus f of z. I'm just rewriting f of z. It's a z bar this time, and there is an over bar over the top, over the thing. So what I get here is minus I gamma over 2 pi log of z minus v. And then here, well, z bar, well, that's good, okay. There's this over bar. I'm going to treat this over bar. So I've got an I here, which become minus I. With this minus, that's a plus. I've got plus I gamma over 2 pi. And I've got log. This z bar over bar becomes a z. And I've got minus v bar. Remember, v is a complex number as well, right? It's the position of this vortex. So that can also be complex, and therefore we have to write this down like this. Okay, and then if I want to simplify this further, I can write down that it's I gamma over 2 pi times the log of z minus v divided by z minus v bar. And that gives me the resulting flow for this vortex. I should have written that it's got a circulation gamma. And for which this line here, y equals 0, is a streamline. So that's our first example. That's the wall at y equals 0. Now we can also look at what happens if we have a wall at x equals 0. And, well, the method is not going to be much different. There's just a slight modification to this formula. So it's w of z. It's going to be equal to f of z. And then here I'm going to have f of minus z bar over bar. What that tells us is that I am actually putting a vortex on the opposite side here of the y-axis. And well, that's the image of this vortex, which is eventually going to impose a vertical wall at x equals 0. Well, let's just check that again. So if we write down that z equals iy, then w of iy equals f of iy plus f of, okay, I've got minus z bar over bar. So minus iy, I'm taking the bar of this thing, and I put an over bar here. So that gives me f of iy here plus, okay, I've got a bar here, so that becomes a plus I. Okay, and plus I, and I've got an over bar over this thing. Okay, and so what I have here is a number. Once again, it's a complex number, and the same and to this number I add the same number, the complex conjugation of the same number. So the result is always going to be a real number. So what we've demonstrated here again is that in this case, well, the stream function, so it's in iy here, the stream function is 0, and therefore that z equals iy is a streamline. Okay, so that shows it. And lastly, we can just also write down an example. So if we write down an example for the very same vortex that we had in the beginning of this lecture, we have w of z. I'm going to rewrite down the whole expression, minus I gamma over 2 pi log of z minus v. and on the other side I'm writing down the same thing, except that I'm putting a minus sign, bar, and an over bar. So minus I gamma over 2 pi log of, so I've got z minus v. The z takes a minus plus a bar, and there is an over bar. Okay? So then, I can continue and write down that this is minus I gamma over 2 pi log of z minus v. This over bar brings me a plus sign here because this I becomes minus I, so plus I gamma over 2 pi. Then in the log, I've got over bar, bar and over bar, which cancel each other. So that gives me minus z, and I've got minus v bar. So if I want to make this expression a little bit denser, I can. And what I get is w of z is minus I gamma over 2 pi log of z minus v over minus z minus v bar. In this video, we've seen how to apply the method of images in two cases. The first one is creating a wall, a vertical wall at x equals 0, and the second one is creating a horizontal wall at y equals 0. This is one typical case, one typical method to impose boundary conditions in the context of potential flows. This concludes this video on the method of images.